Imagine stepping into a building that isn't just, well, static concrete and glass, but something more dynamic,
Hmm.
almost alive, generating its own power.
Yeah, like a skyscraper that's not just amazing to look at, but actually harnesses nature to, keep the lights on.
Exactly.
Yeah.
And that's not science fiction anymore.
Yeah.
It's real.
Which brings us neatly to today's deep dive. We're looking at a true architectural pioneer, the Bahrain World Trade Center, the BWTC in Manama.
Right.
This building really did break the mold. It was the first skyscraper anywhere, globally, to properly integrate large-scale wind turbines right into its actual design.
Not just stuck on the roof, but part of the structure itself.
Precisely. It set a whole new benchmark for what sustainable architecture could actually look like on that kind of massive scale.
That's a huge claim, but it sounds like it's justified.
Yeah.
So our mission today is to really unpack that. We want to get into the thinking behind the design, the clever engineering that made the wind power work, how they later added solar power, which is interesting in itself, and then this really futuristic idea, the digital twin.
Yes, the virtual replica.
Yeah, this digital copy that helps optimize everything. We're drawing all this from a pretty detailed engineering analysis of the building, so we've got the technical backup.
Absolutely. And it's important to remember this isn't just about the tech specs, the concrete and steel. It's about how, innovation and smart design come together.
And cutting-edge tech, too.
And cutting-edge tech, yes. Converging to create something genuinely intelligent and eco-friendly, a potential blueprint, really.
Okay, so let's start right at the beginning. The design. It was done by Atkins, the big multinational firm. And the look of it, it's not just style over substance, is it?
Not at all. It's actually deeply connected to Bahrain's culture. You can see inspiration from traditional Arabic wind towers
Oh.
and also the country's maritime history. That's why you have those two towers, 50 stories high, shaped like giant sails.
And that sail shape is crucial, isn't it, for the energy part?
Oh, absolutely critical. The towers, they reach up 240 meters, and they're specifically angled and shaped to capture the wind blowing in from the Arabian Gulf.
To funnel it.
Exactly. They funnel it, concentrate it right between the two towers. It creates what engineers call a nozzle effect.
Okay.
And that's not just a fancy term. It genuinely increases the wind speed by about 30% before it even reaches the turbines.
30%.
Oh.
Wow. So the building itself is acting like an accelerator.
Pretty much. They get significantly more power out of the same wind just because of the building's shape. It's really clever aerodynamic design.
That's incredible. It's like biomimicry meets large-scale engineering. The wind tunnel testing must have been intense.
Oh, exhaustive, I'm sure. And those tests prove the shape generates this specific S-shaped airflow pattern.
S-shape.
Yeah. What that does is ensure that even if the wind isn't coming perfectly head-on, if it's coming from, say, a 45-degree angle either side, the towers direct it so it hits the turbines perpendicularly.
Maximizing the spin, basically.
Okay. Maximizing efficiency. It means they get a more consistent, powerful energy source, even with slight shifts in wind direction.
Okay, now the really big bit, those turbines. 3 massive ones, right? Horizontal axis like you see on wind farms.
Yes, the classic propeller style. Each one is 29 meters in diameter, huge things, made by Norwin, a Danish company.
And they're mounted between the towers on these huge bridges. That just sounds structurally complex, integrating something that big that moves into a skyscraper.
It presented absolutely unprecedented challenges. The engineering solutions are, frankly, brilliant.
So how do they handle the weight and the vibrations? I mean, turbines vibrate a lot.
Right. They used high-strength concrete, specially treated steel. The bridges themselves are engineered with a pretty sophisticated system to absorb vibrations, both from the wind hitting the bridge and from the turbines operating.
Okay.
And crucially, they sit on these specialized rubber bearings where they connect to the towers.
Like shock absorbers.
Essentially, yes. They isolate the bridges from the towers, preventing that kinetic energy transfer. It allows for tiny amounts of differential movement so the bridges kind of float slightly independently, absorbs stress, ensures stability.
So people working inside aren't feeling a constant rumble or sway from the turbines. That's smart.
Definitely. You wouldn't want that.
And how do they make sure all 3 turbines work well together in that, well, pretty tight space between the towers?
Good question. That comes back to the tower shape again. They taper inwards towards the top.
Right. I've seen that.
That slight tapering helps create a near uniform wind speed across all three turbine
So
levels.
the top one isn't getting blasted while the bottom one barely turns.
Exactly. It simplifies the control systems, the power conversion, even makes maintenance schedules more consistent.
Okay.
And there's an advanced control system linking turbine output to the building's actual electricity needs in real time, adjusting constantly for efficiency.
And safety.
Okay.
Putting giant spinning blades that close to occupied buildings.
Safety was paramount. They have a laser-based monitoring system constantly checking the blade positions.
Lasers? Seriously?
Yep. If a blade deflects too much, gets dangerously close to a bridge for any reason, the system automatically shuts that turbine down, prevents any catastrophic failure.
Wow. Lasers. Okay.
Yeah.
What about resonance? That nightmare scenario where vibrations match the building's natural frequency?
A huge concern, absolutely. They tackled that with a very sophisticated system involving springs and hydraulic pistons within the bridge structure.
Okay.
This setup actively ensures that the oscillating frequencies of the bridges and the turbines always remain different. It prevents any kind of dangerous harmonic buildup. It's an active damping system.
That's some serious engineering foresight. And what's the output? How much power do they actually generate?
The total capacity is 675 kilowatts,
Hmm?
and the projections were for them to provide somewhere between 11 and 15% of the tower's total energy needs.
Which translates to,
Roughly 1.1 to 1.3 gigawatt hours of electricity per year, which is, a pretty significant chunk directly from the wind hitting the building.
that really is substantial. Okay, so wind was the big innovation initially. But you mentioned solar came later. That seems counterintuitive in Bahrain's intense heat. Solar panels usually don't like extreme heat.
You're right, it's a fascinating point highlighted in the analysis. Wind was the star at first, but they did install solar panels, I believe in 2023, shows a continued push for sustainability.
So how do they overcome the heat issue for the PV panels?
Well, photovoltaic technology has advanced. There are cells now that perform better at high temperatures. Plus, the analysis mentions innovative cooling strategies specifically for the panels themselves.
Ah, okay, so not just standard panels bolted on.
No, integrated thinking. And it extends to the whole building. They use high-performance solar glazing on the windows, low shading coefficients, meaning it blocks heat gain effectively while letting light in. Plus other things like strategic shading elements, deep gravel roofs for insulation, energy-efficient lighting. It's a whole package, a holistic energy management approach.
It's not just one solution, it's layers of them working together. Very clever. Now let's shift gears to something really cutting edge. This digital twin. That sounds like more than just a 3D architectural model.
Oh, much, much more. A digital twin is essentially a dynamic virtual replica of the physical asset. In this case, the entire BWTC complex, building, turbines, solar array, everything.
Dynamic meaning.
Meaning it's constantly fed real-time data from sensors all over the actual building, so it mirrors the physical building's operational state almost perfectly, second by second. It's a living virtual copy.
That sounds incredibly powerful. What kind of data are we talking about? And what can you do with this digital twin? What's the big advantage?
Okay, data-wise, it's pulling in masses of information. Wind speed, direction, turbine vibration levels, bridge structural sensors, temperatures on mechanical parts, solar panel outputs, energy production meters. Even data from the building management system, like HVAC performance in different zones, energy use patterns. It's incredibly granular.
Okay, so it knows everything that's happening. What's the most impactful thing it allows them to do?
For me, it's the predictive capability. That's where it really shines.
Predictive, like a crystal ball for the building.
Kind of, yeah. All that data feeds into complex physical models and, crucially, machine learning algorithms.
Okay.
So, based on weather forecasts, the digital twin can predict pretty accurately how much wind and solar energy they'll generate tomorrow or next week.
Which lets them plan energy use.
Exactly. They can simulate how extreme weather might affect the structure, testing resilience virtually before it happens. It can identify ways to reduce energy demand inside the building to match the predicted renewable supply.
Smart.
And the machine learning enables predictive maintenance. It can spot signs of potential failure in a turbine gearbox or bearing before it breaks down.
Ah, saving downtime and costs.
Hugely. It can also find hidden inefficiencies, maybe where energy is being wasted, and even help refine the turbine control algorithms over time to squeeze out more energy. It transforms building management from reactive fixing problems to proactive data-driven optimization.
That really does sound like the next frontier,
Yeah,
making the building truly intelligent.
it is.
Okay, wow. So just to quickly recap the highlights from this deep dive, we've seen how the BWTC's amazing sail design acts like a wind nozzle.
Boosting power.
The incredible engineering needed to safely hang those massive turbines between the towers, including dealing with vibrations and resonance.
The bearings, the damping systems.
It's a smart move to add solar, adapting tech for the hot climate, and then this game-changing digital twin, making the building self-aware and self-optimizing. So what's the takeaway for you listening? What does this all point towards?
Well, I think the BWTC is just a powerful example of what happens when you blend, traditional ideas like the wind tower inspiration with really advanced modern technology. It shows buildings don't have to be passive shells. They can be active players in a sustainable future, intelligent systems that manage themselves. And it makes you wonder, if one building can do this,
What could a whole city designed that way look like?
exactly. What could an entire city achieve with that kind of integrated, intelligent design philosophy? The potential is just immense.
That really is something to think about. Consider how those lessons from Bahrain, the blend of design, renewables, digital intelligence, might reshape not just our skylines, but our whole relationship with the places we build and live in, making them truly part of a sustainable future. What part of this blueprint for tomorrow's architecture stands out most to you?